And with no further ado, I'd like to introduce Mark Wong of Second Quadrant to talk about bidirectional replication.
So scale is another good one to go to, which is a little bit closer, right?
That's true. That's true. That's scale in Los Angeles in
March, the
yeah.
first weekend, I think, the 9th, starting the 9th. Yeah, so I'm here to talk a little bit about bidirectional replication, what the Second Quadrant project. I'll give you a little bit about me. My name is Mark. So I work for Second Quadrant. I've been, I guess, recognized as a Postgres contributor for a little while now. Originally for doing a bit of performance testing on bigger-ish systems. And then I wonder, do people use pgtop anymore these days? A couple? Yeah, I haven't. That thing could probably use a little bit of a refresh. I'm also been a director at the United States Postgres Association, trying to do some helpful advocacy stuff in the U.S. And I'm from Portland. I'm involved in the user group up there. If anyone ever made it up to Portland. So I came down to talk a little bit about MultiMaster Replication, what the BDR solution is, and what to be aware of if you're interested in using that. So how many folks are looking forward to using MultiMaster Replication? How many are using it now? So just wanted to do a quick review. I think a lot of people should be familiar with this general idea, having a single master. One of the particular setups, I think, it'd be good to get some feedback too, but I think one of the particular scenarios that make people interested in multi-master is you have two data centers, made one up in Canada and one up in Argentina. So you got this dark blue guy as your primary system, and anyone who's close to the Canada site is going to have some fairly good response times, and you're servicing people closer to Argentina also. Well, they have to use that primary node up in Canada, and response time's not so good. They're accessing data up in Canada, it's replicating whatever changes are made locally, and then changes get made all the way down to Argentina too, which people will still use as a read-only system. That as long as you have queries that only need to read data, you can access that Argentina site directly. Otherwise, you got to go up to Canada. So I made up some numbers. I'm not sure how realistic 160 milliseconds from Argentina is all the way up to Canada, but just to convey the idea that access is probably going to be a little bit slower than you'd like. So everyone has done a hot standby with Postgres. How many of these issues have you guys had to deal with? Split brain because the standby you had to promote was promoted by accident,
well, 5 of those.
incorrectly on purpose. But basically something goes wrong with a failover. Standby gets promoted by accident. Maybe it took a little longer to get that standby started than you were hoping. Depending on what your situation is, if you were in a state where you promoted that standby, how do you get the other system back? Or what? For various reasons, something catastrophic did happen. Maybe it wasn't so bad, and you could deal with getting that previous system back online. How many folks wish you could write to all the other systems? So that's that's where we hope MultiMaster Replication helps us dealing with all those particular things. Not a lot of text and no reason to read through all of that. Just a definition of the Wikipedia definition of a multi-master system. So these are the things that a multi-master solution isn't something that you can always drop in. One of the important things to you'll hopefully understand before diving blindly in, so to speak, is that there are some things that it's good for and some things that it's not so great at. So the main things that a multi-master solution would be good for is, well, the first thing, unfortunately, is having an application that is designed for a multi-master solution. And what we mean by good is something that is aware of potential conflicts of data being written or updated. In addition to that, one of the other use cases it's good for is having geographically distributed data. So an example of that is, let's say you have customer data on the East and West Coast. It doesn't necessarily mean it's physically separated, but if people on the East Coast are going to be modifying data, it means that there's going to be a subset of that data that is specific to that region. Similarly, if you have customers on the West Coast, users on the West Coast would be hopefully just modifying data that are those customers on the West Coast. So all that data could be living in the same table, it could be partitioned and whatnot. But the idea is that there is a hopefully distinct set of data that different regions are going to be working on, whether or not that data is physically separated or not. Works well for insert-only workloads. So if you have a special use case, you may or may not have a workload that is insert-only, but if you do, that would be one thing that would work well with a multi-master solution. And one of the other things people want out of this is being able to do a switch over, failover in not in the same sense as you would with a hot standby, but if you have an application that works directly with one node because it's the closest one to you geographically, physically, that node goes down, you could just simply redirect that application to another node in another part of the world. So I think the two bigger things that you should shy away from is if you thinking that having multiple writable nodes is going to improve your write scaling. You change data on one node, all that data has to change also on all the other nodes. It's not distributing the work because each of these nodes in this cluster is a full copy of all the data that you have. And one thing that you'll find very quickly if you weren't aware is if your workload is changing data, the same data on different nodes, and that will be immediately apparent on how well the cluster starts performing. So how that looks is that each of these nodes are talking to every single other node. What popular term is a mesh network, I believe. So the more nodes you have, the more communication will be happening between each of these nodes. these requirements are, I think, the requirements that we had for the solution that we wanted to put together in BDR. Not necessarily all multi-master solutions might have these specific goals that they're trying to meet. So we want to make each node accessible because if you're going to have this cluster distributed around the world, you want your application to respond as best it can. So it needs to be able to talk to the node that it's closest to. We want to make sure that if you make a change on one node, all those changes do get propagated back and forth between all the other nodes in the cluster. And for those of you who know more about a little more about the internals of how replication works in Postgres, we know that we can't use physical replication because that will only let you, what's the right way to put it, would only let you have exact copies of one node. Sorry, I can't think of the clearest way to put this. You can't make changes to one node because that has to be replicated all the other ones, and be able to make changes to another node and have. I feel like I'm saying replicated too much, but yeah, forgetting words here.
Well, is it just because of the level at which those right-hand logs actually apply? Like, write these bits to these blocks, and there's not really an understanding above that level where you can merge something else in.
Right. So I think the other way I'll try to put this is, you make an update to one system, you need to logically make those updates so all the other systems, you can't make the exact binary updates to all the other systems because, as David was saying, how those bits are physically laid out on the disks are not going to be the same if different changes are happening on each of the nodes at the same time. One of the other requirements that wasn't true with the original, mostly true with the original release of BDR with 9.4, was that this still had to be Postgres under the cover. It can't be some Postgres fork in the long term. We wanted this solution to be highly available, meaning that if one of those nodes go down, the rest of the cluster needs to be operational to some degree. Well, fully operational, ideally. And then, similar to the bullet above, we didn't want to have some different on-disk format. This needed to be, I think, it's a little oversimplified to say that you need to be able to swap BDR out if you didn't want to use it, but it couldn't be something that was, again, some kind of fork of what Postgres is or is doing on disk. And one of the other goals, if not immediate over time or whatnot, was that the work that goes into developing this BDR solution that we had was gonna eventually find its way back into the core Postgres code. And we try to illustrate some of this going on. So this is something that has been happening over time. If you can imagine, well, I don't know what the lines of code number is with BDR, but as of starting with 9.2, I think the inception of BDR second quadrant, how many years ago is that now? 1, 2, 3, 4, about 6 years ago. There's been a number of things that have come in from the work that's gone into BDR. I think just to name a few of the big ones, the background workers was one idea. So the logical decoding, and even with 10, it's not necessarily what a direct commit. That's not the right word. PG logical wasn't directly committed in the core, but I think a few of those concepts were eventually re-implemented.
Riffs on it.
Yeah. So more to come, hopefully, and I don't know what went into 11, but we'll see what goes into 12 and so forth. So another graphic to illustrate a little bit more about what the current iteration of what BDR looks like is the blue nodes are being the actively accessed nodes in this multi-master cluster. There's also this concept of, I think we call them shadow masters, shadow something, with these conceptually these gray dots, these gray nodes are replicas of the individual nodes. So, the individual nodes. So you can picture each of these nodes being in a different data center, for example. That's one way to conceptualize this. For greater availability for a particular node, if one of these nodes go out, hopefully not the entire data center, one of these other gray nodes can quickly take the place of that down system and continue operating. Yeah.
So that's analogous to a warm standby where you're not directing any queries to it until you switch it in.
Yeah. Although the reality is that these are really not even. I mean, they're still more than a hot standby in reality. These are up and ready to go nodes, but the idea is to treat them like a warm, hot standby. So the BDR solution is actually fairly simple to describe in a nutshell. I mean, is there really more to a multi-master solution than just being able to write to more than one physical system? But there's still a lot to be aware of. If you're thinking about a multi-master solution, you need to put a little bit of effort into figuring out whether it really is right for you. So we'll go through some of the issues that have come up and give you an idea of the effort you might, even if the multi-master solution is right for you, there still may be some effort that you may need to put into your application to make sure that you're really using a multi-master solution properly. So how many folks are familiar with that CAP theorem? The idea that you can have two of three things. So those three things being the C, A, or P, consistency, availability, and partition tolerance. I think, if I recall correctly, this theorem was really meant to be applied to network topologies. So in a distributed system, they don't apply directly. There's a little bit of what's the word I'm looking for?
Impedance mismatch.
Yes, thank you. Yes, that's exactly what I was trying to think of. So how many heard of this Packout Theorem? It is a extension to the CAP theorem that is meant to apply to distributed systems. So it's a great acronym because it's terribly hard to remember how these letters came out. So although it is kind of fun to explain sometimes. So the pack, I think, is a play on CAP. The the way I remember it is thinking what the story is supposed to be. So in a distributed system where partition tolerance isn't one of the things that you can give up, the idea is that you have to choose between availability or consistency. Otherwise, or else, if I'm going to stick to the letters, you need to choose between latency or consistency. So in a distributed system, in a distributed database in particular, you need to, in your design, or your implementation, that is, you need to choose between latency or consistency. So in the earlier versions of BDR, it was the latency that we wanted that we chose to be more important than the consistency. But with the latest version of BDR, you are able to pick whether you prefer latency or consistency between the nodes. So with respect to latency, there are things you do have to remember. The time it takes to propagate data from one node to the other, especially when you want your cluster to be distributed worldwide. Just the amount of time it takes for data to transfer between eastern seaboard to the west coast, across the Pacific, over to Europe. Well, you would think, whichever direction it's going to go. You do have to remember that it is going to take some time for one node to see the data. And the other thing to remember is also how many nodes you have, just because same idea of what I was mentioning earlier about the right scaling. The more nodes you have, the more data that needs to be written, and depending on the path that the data takes, it may take a little bit of time to get around.
So is it the case that the system, the latency of the overall system is basically the latency of the slowest link among masters? Or is it worse than that?
I think depends. So if I'm understanding your question, someone's accessing data in New York, it gets written there. So then the system in New York needs to send the changes over to San Francisco, and it sends it out to Europe. It's not that the cluster waits for it to be written across the whole cluster, unless you decided that you wanted the consistency more than the latency. Then they would show up as they get applied. But yeah, if you were making the system synchronous, then I think you're right that it would be eventually however slow the slowest link was going to be between the whole system.
Is there a concept of, like in BitTorrent or bandwidth multiplication, where the first guy writes to a second guy, and then now both of them are distributing it out, right? So you're effectively getting a power of 2 as you go down. So is in your example, is New York writing to San Francisco and then Europe, and then to all the other nodes, like kind of sequentially or at the same time?
Yeah.
Or once it sends it to San Francisco, both New York and San Francisco know the rest of the nodes inside the cluster and start communicating with them, and kind of you start building it up.
That one node in New York writes to all of them.
Okay.
Yeah, so it's not writing to San Francisco, and then if San Francisco is sending the same updates to the next node, it's the one node that's pushing it out to all of them.
And in the case of sort of a database connection, I know you were like kind of mentioning it before, when a node goes down,
Mm-hmm.
right? All the applications or all the clients that are connected to that particular node, they have to figure out what other node is available and like connect to it, or
Right.
there's some kind of a broker that's sending them.
Right, right. The responsibility is on the application to decide what to do if the node that it's talking to is no longer responsive.
Right, I got it. And what's the granularity of replication? Every single transaction? Or every single write? Like, I'm assuming the whole transaction is done. You're not rolling back transactions across the whole cluster, right?
Right, right, right. You know, I actually always kind of forget this myself in terms. So it's no different than what logical replication is doing now, and I do always get a little mixed up between when it starts to replicate the data, depending on the replication and so forth. But it is the same consideration even in the normal single master primary standby with the logical replication.
So in current logical replication, the replication doesn't begin until the creator of the transaction commits, because it won't even have the decoder, the plugin won't even see the data until the commit happens. That doesn't mean it's committed on the destination machine, of course. It'll start playing it over, and if that link breaks, for example, then the commit will never happen on the destination machine. So.
There are a few things to remember when the node goes down. How many folks have had the joys of dealing with replication slots? Yes. So if one node goes down, BDR is using replication slots. So as changes are happening on all the other nodes, the transaction data is getting saved until that node comes up and starts consuming those transactions again. But at the same time, if you can rest assured that when that node comes up, it shouldn't be missing any of the transactions that have been building up on the other nodes, as long as nothing else has happened to any of the other nodes in the cluster.
So does that mean the destination acknowledges to the master that, hey, I got this, everything's fine?
Yeah. So there's communication that goes back and forth. The one node is keeping track of. So one node is building up the transaction information to send to the other system, and it's waiting for the other system to acknowledge that I've consumed this point in the transaction log.
Okay. It sounds like, how does it handle order? Does order need to be serialized, or is it just a last right wins scenario?
Oh, well,
Okay.
get to that in a little bit.
All right.
Oh yeah. So this is what I was hinting at. While BDR is tolerant of nodes going out, there are limits to that, and that's going to come down to disk space. However much space that you have for where those transaction logs are building up, because once you run out of that space, I think the whole cluster will go down, because that one node won't be able to handle any more changes on that node, and it won't be able to take any more changes. Is that right? Well,
Snapshot too old, basically.
The node will shut down. Typical out of space. The typical out of space handling on the Postgres node. So then all the other nodes that node's going to go down, or you already lost one node, and the next node's going to go down when it runs out of space, saving up data for that node, and it could cause a chain reaction at some point. I mean, not like an instantaneous chain reaction, but all the nodes are going to start backing up more and more transaction logs because more nodes are going down and not consuming them. Yeah.
How do you shoot a node if you need to? Like it's gotten far enough behind that it's starting to be more of a problem than data loss would be?
So you can go to any of the other nodes existing in the cluster to tell the cluster that this node needs to be removed. And when you start working through that process of removing the node, then the replication slots will get dropped, and then that space will be reclaimed. So there's no better way of dealing with that at the moment. If one node is going to go down irrecoverably, and you know that it's not going to be recoverable, then that really is your only solution at that point. Now, and we just kind of talked through this, I think.
Sorry.
That's okay. Notes for later. So one other thing that's probably worth noting is that
Excuse me?
yeah.
I don't understand that first point.
Oh,
If source node goes down and then all the nodes went down. Why is that?
The first node goes down for whatever reason.
Yep.
Any changes to all the other nodes that are going to save that transaction log for the one node with the expectation it's going to come back out. So if that first node never comes back out, then the transaction log is going to build up until space runs out on all the other nodes. That's going to. Sorry, I think I'm not saying that too clear. The transaction log is going to start filling up the disk on all the other nodes. So then the next node that goes down is going to be the one that runs out of space first, and so on. And as more nodes go down, that problem compounds because
there's more transactions waiting.
Right. So all the nodes are saving transaction logs for one node that goes down. When the second node goes down, the remaining systems are now saving transaction logs for two systems,
Yep.
and so on. So if one node goes down, it's going to, I think, snowball is probably a good way to describe it. Yeah. So.
Did you guys look at partitioning schemes for that? Because you can partition like the pending transaction log, right? To say, hey, the first, like if I had like n nodes, this node's going to store
Mhm.
whatever, a fifth of the transactions, the other one's going to store a fifth of the transactions, and so on.
Yeah. So if I'm understanding you correctly, each node, the cluster doesn't share a transaction log. There is no single universal transaction log between the clusters, or between the nodes. Each node has its own distinct transaction log. So there's no sharing across the cluster. I think to the original question about how you deal with this, there's nothing built in for you. It is something that you will hopefully not run into, but making sure that you have some monitoring set up to keep an eye on disk space, for example, the replication lag between the nodes, and having a proactive DVA will hopefully keep the entire cluster from going down, because you can't always, accidents happen for whatever reason or another, right? So a couple notes on security. one thing to remember about this cluster is that it still isn't a single image. It isn't a single database that you're accessing. These really are physically separate databases that are just talking to each other. So having clear policies on how you're going to grant access or who should have access to these systems, because you can set up privileges differently on each of these systems. I think the bad scenario that you want to stay away from is that you restrict someone's access on one node and you forget to do it on the other nodes. So things like that, making sure that you are applying your security policies appropriately on each node. Yeah.
Have people been using this to comply with regulatory frameworks like GDPR?
I'm not sure. Yeah, I'm not sure to what extent people take advantage, abuse, or hopefully use in a good way. But yeah, but I can certainly understand that you have a system that's supposed to be replicating data between other nodes. Unfortunately, it doesn't apply to user roles. Another caveat is that serializable might not work as you think it would across a cluster as it is on a single system. Do folks have need for serializable now? So the thing to remember is that if you're running in a serializable isolation level, that will be honored on the node that you're on, but it won't appear that way with how the locking is granted on the other nodes in the cluster. So that's a artifact, if you will, of keeping the latency down on each of the systems or across the cluster.
You still get recommitted though.
Right. Well,
Partial transactions or anything horrifying like that, do you?
well, the way I would think about it is that locks aren't replicated. So whatever locks that you would normally get, you would normally expect to get granted for whatever transaction you're running. DDL. Well, okay, sorry, DDL is not a good example. With an update, delete, or truncate, you will get the locks that you're expecting to get on the node that you're working on. But just because you are truncating a table on one node doesn't mean that lock is granted for that table for you from all the other nodes. So people are still able to do whatever update, insert, delete on the other nodes, and they would get the locks that they would expect to get granted locally. So yeah, so
But you wouldn't see a partial right.
right. Right.
You might get a right skew anomaly,
Yeah.
but you wouldn't get like you couldn't see a partial.
Yeah.
So, let's say on a subscriber node, well, I guess, something that's receiving transactions. A local operation is running in serializable mode. Could it, in theory, get a serialization failure because of replicated transactions?
Yeah. I think the answer is yes.
Yeah, I would be surprised if it couldn't.
Yeah.
Because, so it's enforced to that extent. But
Right.
what you're saying makes perfect sense because the two sides aren't sharing the serializable lock information between
Right.
them. So
Right.
makes sense.
I mean, it sounds like even in that scenario, you can't really even run serializable at all because you're just going to get write conflicts between nodes, right?
Well, you're already in a situation where you're not expecting a lot of write conflicts. I mean, that's why you picked this solution.
No,
in the first place.
I think, I don't mean to
It's okay. It's okay.
derail, but it means that the the serializable mode, that if you turn on serializable mode on the publishing system, it's, it's not going to pass the serializable mode down to the subscription system
Yeah.
and have a transaction. And so if something would, if you imagine, you suddenly hopped the gap and everything was running on one machine, you could have a situation where it would receive a serialization failure in that scenario,
Yeah.
but it wouldn't because
So-
because it's coming over replication.
So US and UK are both trying to alter the same record.
Mhm.
Well, that's not, serializable doesn't prevent that. That's just local locking. This is serializable is predicate level locking. Where, for example, a select can conflict with an update. So it's probably a rabbit hole that we don't want to go down to talk about exactly how serializable works. But
Especially,
in fact, I think maybe one way of summarizing is the incoming replication traffic is always in read committed mode.
Yeah.
It's never, even if it was generated in serializable mode, it won't be applied in serializable mode on another system. So.
yeah, and the serializable snapshot isolation is also a fun implementation to describe. But
Well, you could probably describe a rights queue anomaly, right? You say, update this table, set everything to false. The other node says, update, set everything to true.
Yeah.
They,
Exactly that.
yeah, they cross, and you're not getting conflicts on records, but you're getting wackiness that you didn't quite expect.
yeah, and we can go into the conflict questions. So I say that one for the last because I figure that would be the most fun part.
It is the most entertaining.
Yeah. So kind of leading into that is one thing to remember when you have more than 3 nodes, or more than 2 nodes really. So I think it's easier to visualize. You have 2 nodes, you make changes on one, they go to the other. You make changes on the other node. They're just kind of going back and forth. And order to some degree is kind of easier to visualize in that scenario too, because they're going to happen locally first before they happen on the other node. So now when you add that 3rd node in there, there is no guarantee on your first 2 nodes are A and B. You don't know if C is going to see the changes on B first or A first, and then it just continues to, the order just continues to become more unpredictable the more nodes that you have. So yeah, now for the fun part. This is an asynchronous system between nodes. We just don't know can't always predict what order things are going to happen in. One of the things that, I forgot how many more of these. Okay, yeah. One of the fun scenarios that happens is when you're using sequences. So to kind of oversimplify one scenario, you do an insert on node A and the next sequence is 10. You do an insert on node B roughly the same time, and it also gives you the next sequence as 10. In the typical conflict resolution, the normal conflict resolution is that the last update wins. Well, you have 2, the last change wins is probably a better way to put it, but you have 2 new rows with the same primary key given to you. How do you resolve that? I think in the latest change that wins doesn't really resolve that, right? You just lost data in that case, for example. If you give the system credit for throwing one of those inserts away just so it stops arguing, the nodes stop arguing between each other. So the way to deal with that particular case is to use what's in the latest, for what we call in the latest version of BDR, a time shard sequence, which is effectively, which is basically taking a combination of the unique identifier for that node and a timestamp to almost always, a very small chance of having a conflict in that, in that case of generating a unique ID that you don't have to worry about those kind of conflicts. Yeah.
So that's a primary key type effect. You would typically be used as a primary key.
Right, right.
What actual data type is that?
I think, oh, that's a good question actually. I know it's in the documentation. What I don't remember is if it's a integer type, some kind of integer type, or whether it's a UUID string type.
Mm.
But using the, I forget the name of that extension that generates the UUIDs for you.
OSSIP?
Yeah.
OSSB?
Right, right. So that's also another alternative to have a, just have the function generate a UUID for you instead of using what we're calling a time shard sequence.
I guess you could also partition by node ID or something.
Right, right.
Instagram also has a function that they use that's effectively the same thing. It encodes a shard ID into it. The advantage of it over UUID is they're still time orderable within a single shard, which a UUID, of course, is just random.
Right, right, right. And that was one of the things that we started recommending to folks, because originally that first version of BDR, how many folks have tried BDR or are using it now? So in that first release of BDR, there was a what we called a global sequence, was basically managing the one counter across all the clusters, which turned out not to be the best solution for managing a sequence across clusters. So then what we started recommending was that, just like you were saying, well, still use the counter, but increment it in a way that keeps it unique across for that particular node. So while that worked, where things started getting, still wasn't totally solved, were when you're adding another node, what if you didn't partition that for enough, with enough, what's the word I'm looking for, buffering? Is that really the best word? But then you'd have to do it all over again, and even if you were in a situation where you weren't doing that to begin with, kind of doing it on the fly, sounds like it might work, but sometimes mistakes can happen trying to even set that, getting that partitioning of that sequence in place on a live system can sometimes cause some headache. So, I mean, ultimately, being able to rely on the system to set that up for you without worrying about making a mistake is the way we want to go. So some other things to hopefully alleviate some worrying is that BDR will log when conflicts happen for you. So you don't have to worry about, oh, did something happen? What did some data need to get, or how was the conflict resolved? So being able to look through logs and see that, knowing that what has happened can give you some peace of mind to a degree. But as you might imagine, the more nodes that you have, it probably is more likely that more conflicts will happen, and keeping an eye on that. You want to try to monitor the logging to some degree to keep an idea how many conflicts are occurring, because resolving conflicts isn't necessarily a trivial amount of work. you have changes on one system, you can you already know that that's writing that all to all the other nodes. Then when you have conflicting changes, once you figure out what gets resolved, then you have to resolve that on all the nodes, on top of the original writes that happened to all the nodes. So for performance reasons, even though you may feel confident that the system is resolving any conflicts for you, you don't want to just let it happen just because they're being taken care of automatically for you. Being a little proactive and trying to mitigate the amount of times the system needs to resolve conflicts will be good for a healthy cluster. Yeah.
And is it true that, like PG Logical, a conflict in this case means constraint violation? That's what a conflict means to BDR.
I guess I wouldn't necessarily. I think the constraint violations are the tougher ones to deal with. I mean, it could just be as simple as I'm thinking of a banking situation. You update the balance on one node and you update the balance on the other node.
How would it know?
Oh, what do you mean?
How would it know that it's a conflict? How would it know that there's an inconsistency in the cluster?
So
Because the updates can hit two different masters at the same time, and then be based on the replicas to each other, and they overwrite each other.
right. So
And then you have split brain.
the simplest case is saying update the balance to be 1,000. Actually, the banking example is probably actually not a good one because this doesn't make sense. Maybe age is better. If I'm setting your age to 18 and someone else set your age to 20, which is correct?
Yeah.
I guess the question is, how does BDR detect that situation?
Yeah.
If it's like, let's say it's a single line update, so it's running its own transaction.
Yeah.
One side does it, the other side does it, they get pushed over across.
Right.
One receives the data, goes, oh, okay, whatever, and applies it to its copy. The other one does the same. Since presumably they don't ping pong, they don't then turn around and write back to each other.
Right. Right.
So in this case, is that just for the application to sort out?
So BDR will pick the most recent change, whichever one happened to be.
Okay, so across some kind of, basically, assuming everyone's clocks are in sync.
Yes.
And it'll literally the wall clock.
What happens if
Right.
they're
Most
at the same
recent wall
time?
clock.
Then it will then do it by node ID. Actually, then it will just actually pick. Effectively, it picks one node to always win.
And then it will log that as a conflict. I see two timestamps, two transactions with the same timestamp.
Right.
That is a conflict. Log it, and then I'll just pick one to go with.
Right. Right.
Okay. So, how confident are we that this type of conflict resolution is deterministic across all nodes for all scenarios?
Oh, it's. I think we're pretty confident in that because we know. I think we all know that clocks can only be so much in sync.
Yeah.
But then each node does have a unique identifier.
Yeah.
So knowing that the nodes will have a unique identifier, then we can just pick whichever one. I actually forget if it picks the one that sorts first or sorts last at that point, but it'll pick one of the nodes depending on what its identifier are as a order.
So is it keeping some sort of cache or something like that? Of saying like, oh, I'm seeing these come through, and then I can compare the transaction against the other.
Oh,
what I saw
that's
previously.
if I'm understanding the question, that's the transaction log.
Okay. So it's querying the transaction log to understand things.
Well, yeah. It's part of the apply process of the
Okay.
transaction logs.
Okay.
So going back to my oversimplified example of the updating that one field, there's this concept. The text calls this a data type, which I think depending on the system, it is a real type. But in Postgres or in BDR, right now it's really more of a concept. This conflict-free replicated data type can be implemented as a type of what did I call it? Log-style bookkeeping. So I think the bank example is a little bit better in this case. You have whatever your balance of your checking account is, instead of when you're depositing money into it, instead of I think you can imagine updates happening one of two ways. That an update is going in with what the new value is supposed to be. So if you had $1,000 and you're depositing 100, you could say update set to 1100, or you can say
Add 100 and you get a community of operation.
right. Update, just add 100 to whatever the current value is. So the idea is without having a data type that did that under the covers for you. The idea is to have another table that stored the changes as rows in the table. So then it didn't matter whether it was added, if someone was depositing money, subtracting money, so all at the same time, whatever the two deposits happen at the same time. By having another table have a row of each individual change, and then being able to sum that up makes the how David put it, having the changes communicable. Commutable.
Yes.
Yeah, I need a little bit of math terminology review. But having a way to sum that all up, all the changes without having to worry about the order that they happened in, is one way of getting around some of these conflicts, some of these update insert. Those are just update type conflicts, I think.
This vaguely reminds me of what a time series database does, where you create a view, you create a construct that each one calls it a different thing. That's effectively a window over data that comes back as a different value or a scalar value, like the last. That's so you say, well, give me the last six weeks of this value, and it's continually keeping it up to date.
Yeah, I think for some reason Redis does this. That's what Redis does.
You're talking about CRDTs right now?
Yeah.
That's different than my understanding of them.
Oh.
They're more, so my understanding is that, let's say you have like a document and there's an address in the you have like addresses in the document, right? And so you delete record 3, and so the CRDT would record in the log -3.
Right.
And then you add something, and then it would say plus this. But the way that it keeps the addresses of the document is such a way where you can delete and add to it. And there's some trade-offs for that. But basically, it's this notion of if you have the log of those alterations of the document, you can reconstruct the document anywhere. And those transactions can also happen out of order.
Right.
The replication can happen out of order and you'll still get to the final state.
Right.
Assuming trade-offs. That's my understanding of CRDTs.
Right. Yeah.
Okay.
So was my
Well, I think with the time series discussion, I was like, I was lost as to how they would be directly applicable. But yeah, I'm
Let's
Maybe.
maybe we can move this to hallway
Okay.
track and,
Oh, are we getting close to?
yeah.
Okay. Yeah,
I
yeah.
don't
So,
mean to.
so I think that was what was considered operator based. The state base is a little fuzzy to me, but
Yeah, maybe that's the example you're thinking of.
yeah. So then, as much fun as it is to talk about conflicts, then what I wanted to leave you guys with was, for those of folks who have played with the first version of BDR was the one that we open sourced back in 2014. Since then, we have kind of closed it off in order to we needed to sorry, words are having trouble for me right now. For the amount of money that Second Quadrant has invested in the development, we needed to try to recoup some of that with selling to support for some customers. But we're up on the third iteration of BDR 3. There is no date yet of when we might open source that, but it'll be somewhere down the road. But as of BDR 3, folks heard of PGLogical? The BDR 3 is built upon PGLogical, and the current version of PGLogical will be released sometime in early 2019. And we'll leave it at that for now. Thank you.